All right, let's jump right in. Today, we're doing a technical breakdown of one of the most critical and honestly, most misunderstood procedures in engine assembly, the head bolt torque sequence.
Yeah, for sure. This isn't just about making bolts tight. We're talking about managing some really immense forces and the material science needed to prevent a catastrophic engine failure. It's pure engineering.
So, we'll start with the fundamental physics of clamping force, then get right into the correct process. That means staging and bolt types. After that, we'll get into the failure modes, what actually happens to the gaskets, and how a head can warp. Then we'll cover diagnosis, recovery, and wrap up with the tools and practices that are absolutely non-negotiable.
Okay, let's start at the beginning, the first principle. At its core, this whole thing is about achieving a perfectly uniform clamping force.
Exactly. You're trying to contain thousands of psi of combustion pressure between these two huge castings, the head and the block, and neither of them is perfectly rigid. That's the engineering problem we have to solve here.
And this definition right here is key. It's a prescribed process. Both the order and the multi-stage application of that torque are specifically designed to spread that load as evenly as possible.
And that's the part people miss. This isn't just some best practice or a guideline. The torque sequence is as much a part of the engine's design as the piston rings are.
Right. And that gets us to the question every new tech asks. If the goal is just to get them all tight, why does the pattern even matter? Why can't you just zip them down in a circle or work from one end to the other?
Because the cylinder head casting isn't infinitely rigid. If you fully torque down one bolt on the end, you've just created a pivot point. The head will physically bend. We're talking thousandths of an inch, and it'll crush the gasket in that one spot while leaving these tiny little gaps everywhere else. The entire goal is to apply that pressure symmetrically from the center out. And this image here shows the engineering solution to that very problem. It's almost always a center-out cross-pattern sequence. You start at the core, right between the cylinders where those combustion forces are at their highest, and you methodically spread that clamping force out toward the edges. This minimizes distortion and makes sure the gasket sees a uniform load across its entire surface.
And this becomes exponentially more critical with modern aluminum heads. The materials science is what's important here. Aluminum has a much higher coefficient of thermal expansion than cast iron, so any stress you lock into that head by using the wrong sequence just gets magnified as the engine gets up to temp. You're basically engineering a failure right from the start.
Okay, so that's the physics. Now let's get into the practical application, the process itself. Understanding the theory is one thing, but the execution is everything. This is the how and with what.
Right, you never ever go straight to final torque. The process is always done in stages. The first pass is just a snug pass, maybe 15-20 Newton meters, just to get the gasket seated evenly. The second pass takes you to about half the final spec, which lets the gasket compress and the hardware settle in. Only then do you go for that final torque value or angle of turn, following the sequence every single time. And the hardware itself is just as critical. You absolutely have to know if you're working with torque to yield or TTY bolts. They're engineered to be permanently stretched, right into their plastic deformation range. Now, this gives you an incredibly consistent clamping force, but it means they are one-time use, period. Reusing a TTY bolt isn't saving money, it's just guaranteeing a comeback.
So, let's talk about the mechanical consequences. What actually happens down at the sealing surface when you ignore the correct process? Well, modern multi-layer steel gaskets, MLS gaskets, they're complex. They have these embossed beads that are designed to act like little tiny springs. An incorrect torque sequence physically crushes some of these beads flat, just destroying their ability to seal while it leaves other areas undercompressed. This creates these direct pathways for leaks, and the fire ring, the part that contains combustion pressure, is always the first thing to fail.
And the forces we're talking about are huge. Peak combustion pressures can hit 1,500 psi or even more in a modern engine. At that kind of pressure, a gap of just a few thousandths of an inch isn't a leak, it's a cutting torch. It will literally erode the gasket material and even the aluminum of the head itself.
This number is just as critical. For most aluminum heads, you're looking at a maximum allowable warpage of about 0.05 of a millimeter. That's roughly 0.02 of an inch. An incorrect torque sequence can easily distort a head way beyond that tolerance, and at that point, it has to go to a machine shop for decking. There are no exceptions. And this image here is a perfect example. Yeah, the principle is center out, but the exact pattern is specific to this engine's design. Look at the path it takes. 1, then 2, then 3, then 4. It's a precise, engineered pattern. You don't guess this. You get it from the factory service manual. Deviating from this locks in stresses you can't see until it's way too late.
So let's say the mistake was already made. How does that failure actually present itself? Let's talk diagnostics. Exactly, because these internal mechanical failures will always show up as clear, observable symptoms.
You're going to see the classic signs of a blown head gasket, but they all trace back to that initial clamping error. Bubbles in the coolant reservoir? That's combustion gas getting past a compromised fire ring. That milky oil? Coolant is breaching a seal into an oil passage. Misfires on adjacent cylinders? Well, that's compression leaking between them across a crushed part of the gasket.
Okay, so the diagnosis is a blown gasket from an incorrect install. What's the recovery plan, and what other variables do we need to control to make sure this doesn't happen a second time?
The recovery protocol really depends on when you catch the error. If the engine was never started, you might be okay. You still have to pull the head, replace the TTY bolts and gasket, and check the head surface for flatness with a good straight edge. But if that engine has been run, and especially if it's overheated, you have to stop. That head must come off and go to a machine shop for professional measurement. There are just no shortcuts. You know, here's another variable that trips up even experienced techs: thread lubrication. A torque wrench doesn't measure clamping force, it measures the resistance to turning. And that resistance is a function of bolt stretch plus friction. So if the manual specifies oiled threads and you install them dry, a huge percentage of your torque reading is just overcoming friction, which means your actual clamping force is dangerously low. The spec for lube or no lube is not a suggestion.
Okay, that brings us to our final section here, the tools and best practices. These are the absolute non-negotiables for doing this job right the first time.
Look, this is not a job for guesswork or cheap tools. You need a calibrated torque wrench, and you need a torque angle gauge for any engine with TTY bolts. You also need a thread chaser, and I mean a chaser, not a tap, to make sure the block threads are perfectly clean.
For sure, but the single most important tool on this bench is the factory service manual. It has the manufacturer's specified sequence, the torque values, the lubricant. That document is the foundation for the entire job.
And let's just be crystal clear on one last thing. Never, ever use an impact wrench to install head bolts. It delivers these violent, uncontrolled shocks. It's physically incapable of giving you the smooth, progressive clamping force that the engineering requires, and it makes any torque plus angle spec completely meaningless. So I guess the main takeaway is this. The torque sequence isn't just a list of steps. It's an engineered method for controlling stress distribution in the core of the engine. Getting it right means you get a durable, reliable seal. Getting it wrong creates a hidden failure that's just waiting for a little feet and pressure to reveal itself.